Hello everyone. My name is Ayodhya Ratnayakar. Today, my teammate Tusit Visidargamage also joining with me to talk about house price prediction using advanced regression techniques. Competition we have chosen from Kaggle competition. It is our final project. And let's talk about the data set we have chosen and how we do the modeling and how we do the predictions. Let's go to the agenda. Today's our agenda is talk about the project overview, data set overview, and we will discuss about how we clean the data and do pre-processing before we do the modeling, and feature engineering techniques and data analysis step. And also we will show at the end we will show you all how we do the coding part as well. Let's go to the project overview. Our objective is to build predictive regression model that accurately estimate house price using Melbourne Housing dataset. This project is aligned with the Kaggle competition named as House Price Advanced Regression Techniques. Next, I would like to talk about why we chose this dataset. While the competition provide the different dataset called AMS housing dataset, we opt out that and we start using a separate dataset. It's because of two reasons. One is in the program we advise to use a dataset which doesn't have a available solution online. So we choose Melbourne Housing snapshot. Going forward in the slide, we will provide the link to the dataset as well. Next, we would like to talk about what are the tools and techniques we have used. As programming language, we use Python, and also we use the Pandas library, NumPy, MATLAB, and also Seaborn, scikit-learn, and XGBoost. There are a few other libraries as well. Going forward, we will be discussing about that as well. So next, I would like to talk about the dataset overview. So as I mentioned earlier, we have chosen Melbourne housing data snapshot from Kaggle, and link is provided right here. This dataset contains historical property sales data for Melbourne, Australia. It includes detailed information such as location, number of rooms, type of property, and land sizes, and year build, and also how many rooms, how many bathrooms, and what are the how many living spaces are available for that property. So those are the features from the dataset. If we talk about the dataset dimension, we have in the dataset we have chosen had 13,329 records, and total features were 21 features. For this data analysis and modeling project, we have chosen price as our scalar target, and that's represent in Australian dollars. Basically, the range of price varies approximately 85,000 to several million dollars, Australian dollars. So next slide, I would like to talk about how we did the data loading. Step one was we use the API key to download the dataset from the Kaggle website, and that was a zip file. We unzip it and extract the data into Pandas data frame. So in this snapshot, we can see the first 5 rows of the dataset. Next step was data cleaning and processing. First of all, we have go through the data set and identify if there are any missing values. We were found like 4 main features with missing values. Those were building area, a year of build, and council area and car. So we have to come up with a plan like how we going to treat the data set. So what we decide were we actually fill the missing values for year built using the column median. And we drop the rows because for the car column, which has null values, there were only 62 rows, so we have dropped that. And when we are building our data model, we decided that building area and council area may play a big role in feature analysis, so we actually opt out those two columns as well. After that, we applied log transformation to the price, and also we converted the data into all the data into number like format in order to process the data properly. Um, After we do all the cleanups, we start doing some data analysis using exploratory data analysis technique. Actually, this is excellent way to understand the data set before we building a model. So since we are using the Melbourne Housing data set, we generate comprehensive EDA plans using multiple plots. In this presentation, we'll go over a couple of the plots we have created, but at the end, we can go through all the plot diagrams we created for the entire analysis. So this slide, the first one we see here is the distribution of house prices. In this histogram, we are looking into how many houses fall into different price ranges. What that means is in the x-axis, we show the price of the house price range, and y-axis, we show the number of houses that fall into each pricing range. So if you see the bottom line, we see different baskets we created, like for example 100 to 200, 200 to 300. So each category we will count like how many houses are falling into that. And also when we look at this histogram, it shows if price was keyword, which means that there are fewer homes, like most of the homes are cheaper, but fewer are extremely expensive. In the next slide, we will have two bar charts next to each other, which represent average price by suburb. In the x-axis, we shows the names of top 15 suburb with the highest average house price. Y-axis, we shows the average house price in each of the suburb. Actually, this analysis is helpful to find expensive versus affordable areas, and also it shows us how location effect for house prices. It will be important for investors or buyers, and also suburb with unusually high average price may have luxury properties. That's why we see the earlier diagram, there was a skewing to the mean. And also business decision making, we can use these diagrams to find out which area or which part of the district is more suitable for investors or buyers. The next pie chart we shows how house type distribution looks like. So in this diagram, H represent house or a cottage or a villa, U represent unit or duplex, and T represent townhouses. So in here we can see a majority of the uh, pie chart is house and cottages and villas, and very less townhouses are available on that particular area. In this slide, we have actually two diagrams created for price versus number of room comparison and price versus car spaces. If you go to the if you look at the first diagram, we can see the number of rooms on the x-axis, and y-axis we can see how price vary for each room count. In the other diagram, we can see the how price versus number of car spaces vary. Usually it's looked like a box plot, but and you can see how x-axis with 0 to 3, 0, 1, 0 to multiple integer numbers that represent how many car spaces in the for the house, and y-axis shows the distribution price of each groups. By looking at this graph, we can see houses with 2 car spaces might have higher median price, and this that we have seen like most of the properties fallen onto that category. There are fewer properties with more than 4 garage spaces. And next plot diagram is actually we created this to show like how the properties are located in that area. We use the longitude and latitude feature to describe this, and each plotted each property as a point. And also we can observe the dense of the cluster by looking at the dense of the clusteration. We can see that most properties near the Melbourne Central Business District. Rest of the properties are scattered around the other area, but most of the properties were based on the CBD area. And the next slide, we have number of sales over time. We actually generated these graphs to show how the property prices varies. And the one below, we can see the correlation heat map. Correlation heat map measures the relationship between two numerical variables. It tells us whether and how strongly they are connected. So in this diagram, basically like positive correlation means that there are when one variable is increased, the other variable also tend to increase. If a negative correlation, that means one variable increase, the other variable tend to decrease. No correlation means there's no prediction in between two variables. In this map, dark blue means strong negative correlations, light blue means weak negative correlation, and white means there's no correlation at all. Dark red means strong positive correlation. Light red means weak positive correlations. The next slide we have actually use number of features. Here we see four different features. How that vary with the average price. So we have chosen number of bedroom, suburb area, number of room and car spaces, and generated this bar chart. And next, we would like to talk about the main part of this project, which is model selection. We decided to pick couple of few models and then try to create that model and train and see how that impact and which model is give us the most accurate results. So we have chosen bridged and lasso regression, and also we use the decision tree, random forest classification, gradient boosting, and linear regression. Linear regression was the simplest one. The first two, ridge and lasso, also the more close to the linear regression models. But we we created model each and every model, and then finally we did the analysis to determine which model is more effective. Also, as an evaluation strategy, we are using the variance explained by the model, and also we calculate the absolute mean error for each and every model. From this place from here onwards, my teammate Tuzit will explain how we create the models and how how the classification looks like. Thank you so much for listening to me. Let's pass the PowerPoint presentation to Tuzit. Thank you.
Thank you, Aida. Moving on to our model phase, we began with linear regression. Our aim here was to predict house prices using a straightforward and interpretable model, establishing a baseline for performance comparison. Why linear regression? So it's easy to implement and interpret, providing clear insights into how each feature influences price through its coefficients. It's a solid straight point, especially when relationship between variables and roughly linear. Our modeling approach involved using multiple linear regression with all numerical and encoded categorical features. We also applied pre-processing steps like one-hot encoding for categorical variables and um, imputation and scaling for numerical values. Next, we explore ridge regression. The R-square for this model is 0.680, indicating it explains 68% of the variance in the data. While it performs reasonably well, it doesn't quite match the performance of random forest or XGBoost. The MAE and RMSE are moderate, suggesting Ridge is less accurate than the ensemble methods. But in essence, ridge regression serves as a good baseline, but doesn't capture the data complexity as effective as a random forest or XGBoost. Now let's discuss lasso regression. The R square here is 0.678, very similar to ridge, showing only a slight difference. However, the MAE and RMSE are slightly higher than ridge, indicating that lasso has higher errors. Therefore, lasso is the less favorable choice compared to ridge among the linear models we tested. Essentially, lasso performs similarly to ridge, but with slightly high score metrics, suggesting it may not be the optimal choice for this dataset. Let's move on to the decision tree regressive. The R square for this model is 0.644, which is lower than the previous linear models, indicating that it explains less of the variance, only about 64%. The MAE is right here, MAE and RMSE are values the lower than the previous one. So these errors values are relatively high, suggesting that the decision tree might be overfitting or not effectively capturing the underlying patterns in the data. While decision tree are interpretable, they don't perform as well as the ensembles methods like random forest and XGBoost, making them less ideal for this prediction task. Here, we use random forest regressor to improve predictions accuracy and capture nonlinear relationships by leveraging an ensemble-based approach. Random forest is beneficial because it handles nonlinear relationships and interactions automatically, is less sensitive to outliers and noise, and reduce overfitting through bagging. It also efficiently manages both numerical and categorical features after encoding. Our modeling approach uses a random forest regressor for the sklearn assembly library with feature processing include one-hot encoding for categorical variables and median imputation for missing values. Ultimately, random forests provide the best overall performance in terms of R square and error metrics, making it the most suitable model among those we tested so far. Finally, finally, we implemented the XBoost regressor to leverage a high-performance gradient boosting algorithm, aiming to further enhance predictions accuracy and model generalization. XGBoost is adventurous due to its gradient boosting framework, optimized for speed and performance. It handles nonlinear relationships very effectively, and it robust to missing values, outliers, and multicollinearity. So it also supports regulations to minimize overfitting and widely used in data science, computing, and real-world applications. And our modeling approach used the XGB regressor from the XGBoost library, which pre-processing similar to previous models, including one hot encoding for categorical variables and median imputation for missing numerical values. And in conclusion, XGBoost stands out as the best performing model, achieving the highest R square and the lowest MAE and RMSE. This makes it the most accurate model and one we recommended for future predictions. Random forest is the second best, demonstrating strong performance with a good balance of accuracy and interpretability. The other models, including Ridge, Lasso, Decision Tree, and Linear Regression, were less effective but could serve as baseline models. It's worth nothing that Kane also showed moderate performance, but still lags behind ensemble models. And I'm passing to my teammate Ayodhya to go high-level work through in our code. So she's going to take the screen from here on. Thank you.
Thank you, Tasit. Actually, we have covered most of the steps we have done during our project, but I will roughly go through the steps we have performed performed in order to create those models. As the first steps, what we did was we actually used the API key, Kaggle API key, to download the file, and we have downloaded Melbourne Housing snapshot. And it was a zip file, so we have unzipped it and then loaded data into pandas dataset. So here we can see the first 5 rows we have right after we load the data. And next we started doing analysis of the dataset. First of all, we check if there are any null values in each column. So we have find out that these are the features we have. Like we had actually 21 features. Out of 21, we have a couple of actually 4 features with null values: car, building area, year built, council area, and with null values. So as we discussed earlier in the presentation, we treated those, and then we imported all the libraries that we will be using during the data modeling. After we identified and treated the null rows, we dropped the rows with missing target. That was our target. Our target was price. So if there's any row without price information, those have been dropped. And then we start doing the feature engineering. For example, we did extract the year out of date, and we dropped unused columns as we discussed earlier. And then we separate the feature and target x-axis and y-axis coordinates. And then we start doing the categorical and numerical feature analysis. And we do the pre-processing for numerical data. After that, we do the pre-processing for the categorical data. After that, we do the bundle processing. Once we're done cleaning up and doing all the processing, we start we check if there are any duplicates in the data set. So we found out there are a couple of duplicates and we have removed those duplicate rows. From here onwards, we have created different types of plots and diagrams to analyze the data set. Since we have gone through that during the presentation, I won't do in detail discussion. After we do the data analysis, we start doing our data modeling. First, we start with the random forest model, as Tusit explained. We created the test trained data set and create the pipeline for the random forest classification, and we defined the hyperparameter grid. After that, we actually build the model. So once we build the model, we did the predictions and evaluation. After that, we calculate how that model behaves. So as he explained earlier, we got the R square average 81% for the random forest classification. And we have like quite a reasonable error index for random forest classification. Likewise, we have created a model for XGBoost. Ridge regression, lasso regression, and decision tree. So all the and linear regression. After we analyze all of these models, we as he may explain during the presentation, we conclude that we got the best result for XGBoost. So that's the model we are planning to use going forward if we are doing the feature analysis on this project. This is basically what we have completed during this presentation. What we are planning to complete during this presentation, and we will be uploading our code to the Kaggle competition. So we are looking forward any comments from the Kaggle site if you have any. And thank you so much for listening to today. Have a great day, everyone.